Good morning. Today I will start amine system for gas sweetening, and we will do some calculation also, the volume calculation, flow rate calculation, and we will cover this amine separation part. Then we will start a gas dehydration part. If you have higher amount of water content or water vapor or water particle content, so you have to remove that one. So first amine removal, amine, using amine you have to remove sour gas. So sour gas implies H2S basically and CO2, okay. But in certain gas only CO2 is there, H2S is not there, okay. H2S is not there, only CO2 there, then this will be called as sweet gas, okay. But if you have both H2S and CO2, then it will be sour gas, okay. So during amine process you have to remove sour gases, and there are different methods to remove sour gases, but we have already seen that if we have iron sponge or other adsorption method, using that technique also we can remove sour gases. Sour means acidic gases. Acidic gases if you have, then there will be certain issues such as corrosion, there will be hydrogen pitting, and corrosion, hydrogen pitting, all these are problem. And H2S, if you have more than certain amount, then again it will be a health hazard. Let us say if you have more than 500 or 700 ppm H2S in air, then instant death possible. But if you have less than that, maybe one very low amount is there, maybe you can sense hydrogen sulfide, H2S, pungent gas will be there. If you have more than certain amount, then actually your sense will go, because it will be covering your breathing breathing organs, okay. Then after certain time, if you have more than certain amount, then it will be affecting your brain also, it will be senseless actually. So if it is crossing up to, say, gradually crossing up to more than 700, 500, 700, then instant death possible, okay, because their breathing organs will be covered using cough, and lungs will not work, brain will not work, finally it will be dead, okay. So if you have hydrogen sulfide in your gas, you have to remove. Small amount is there, traces there, still you have to remove, and if you have higher amount, then that can be disaster, okay. So how to separate amine? So you had one contactor column or reboiler column, I will draw straight line actually. So contactor column, or this is called absorber column, absorber column. So what happens, you give sour gas mixed with your actual natural gas, okay. So sour gas entry is here, then lean gas should be going out, lean gas or sweet gas, we do not say lean gas or the sweet gas, okay. Sweet gas will be going from top. And what happens, lean mixture of amine solution, mixture you inject from top, and there will be several trays, okay. This is called amine trays, okay. So you create lots of bubbles, okay, and when sour gas is moving up, it will be mixed up with lean amine mixture. Lean amine mixture will be rich amine mixture. Rich amine mixture means it is having more H2S, okay. H2S will be reacting with lean mixture of amine, and then it will go out from the bottom, okay. So this is rich mixture of amine, rich mixture of amine, okay. So this rich mixture you got, that is having lots of H2S, CO2, okay, because it is reacted. Now every time you cannot buy from market and you cannot use, you have to reuse this rich mixture as a lean mixture. How to do it? Then you have to heat here using high temperature, you give temperature here, okay. So reboiler or regenerator column will be there. So I am not drawing separately all these items, so there will be, I will show separate picture or separate figure. Regenerator, okay. So using regenerator, you are producing lean mixture of amine. Lean mixture of amine means low amount of H2S and CO2, okay, almost negligible. So that again you put in contactor column, separate or absorb your sour gases, okay, and sour gas absorb, pure gas or sweet gas you take from top, rich mixture you are getting, you heat here, you give heat. Okay. So when heating, so that compound will be broken, and your lean mixture will be passing through contactor column again, and if we have H2S, that H2S part or sour part, again you put through another separation system. So from there you get sour gas. Okay. So in that case you have to add heat actually. At cold temperature it will be absorbing. Okay. So the amine contactor column will have a temperature lower. Okay. At lower temperature it will be absorbing. At higher temperature it will be releasing H2S. Fine. Okay. So amine absorber, normally it will have 20 to 24 trays. Okay. There will be trays. Okay. So in tray the amine solution will be there. When it will be bubbling up from bottom, it will be mixed up. Okay. When mixing up is happening, it will be releasing all this H2S, and pure sweet gas will be going out from your system. Flash drum retention time around 2-3 minutes. Okay. So there will be flash drum here. Okay. 2-3 minutes retention will be there if any hydrocarbon is there in the gas. So the hydrocarbon will be settling. Okay. HC. This is rich mixture. Okay. So rich mixture going out, it will be going through flash drum where extra hydrocarbon will be moving out from the system, and gas will be going to reboiler section. Okay. Amine reboiler section will go. So reboiler section what will do? Boiler, the term says boiling, right? So you need heat there. So you are heating to amine stripper which drives off the acid gas. So acid gas you are removing. Okay. Reboiler temperature in a stripper operating at 10 psig can be assumed to be 245 degree Fahrenheit, 20% amine, and 250 degree Fahrenheit for 35 degree amine. Okay. So dimethylamine like this. Amine stripper, heat to reverse chemical reaction with CO2 and H2S. Okay. So whatever contactor column reaction was there, here you are doing just reverse reaction. Okay. The stream acts as a stripping gas or removes acid gases. Overhead stripper and reflux accumulation. So these components also will be there. So rich and lean mixture heat exchanger will be there. Now you have okay, I will draw here on the top. Okay, you have contactor column. You are getting rich mixture. It will be going to flash chamber. Okay, flash chamber. Then it will go to reboiler section. Okay, so this temperature is lower, right? This temperature is low here, and after reboiler, when it is going out after releasing all this H2S, the amine part, so it will have higher temperature. Okay, so temperature high, it is having lower temperature. So what you do? You use one heat exchanger here. What this heat exchanger will do? Heat exchanger will increase the temperature coming, the fluid coming from your contactor column is going to boiler section. It will take some heat, and whatever heat is there in the exit fluid from reboiler, temperature higher. So that temperature will go down, because in contactor column, I told CTUR. Okay, in contactor column it will be low temperature reaction. Okay, so you have to reduce temperature. So if after reboiler, if temperature is very high, that you are not putting into your contactor column, you have to reduce temperature. But again, if you are wasting that heat, you can use any condenser, you can waste also, or you can use that heat to increase temperature of the inlet fluid of reboiler. Okay, so you can reuse the heat, so you are increasing system efficiency. Okay, one way reboiler, whatever temperature, high temperature is there, you are reducing, so you got some extra heat you are giving to inlet fluid, so that reboiler fuel cost will be reduced. Fine. Okay. So amine cooler. Now after heat exchanger, you put one cooler also. Okay. Why? Because still some higher temperature is there. You reduce temperature, so that reaction will be proper in contactor column. Okay. Or absorber, reaction will be proper if you reduce temperature. So before putting into contactor column or absorber column, you are using cooler to reduce temperature. So that temperature, that heat, whatever removing, that you may not use. But before that cooler, you are using that heat, that is you are exchanging heat, okay, from lean mixture you are taking heat, you are giving to rich mixture, then you are putting into boiler, and lean mixture with lower temperature it will go to cooler section, cooler will be reducing further temperature, then you are putting into your absorber section, okay. So amine cooler will be fan, small simple fan cooler, lower amine temperature before entering to absorber, okay. Lean amine temperature should be 10° higher than the sour gas entering to the absorber, okay. So temperature have to reduce before entering into your contactor column or absorber column. So here you can see the detailed picture. I said like one absorber system is there, okay. You can see this one I am drawing using my red pen. So these are trays, okay, this is one tray. So many trays will be there. They have shown one tray, and this is rich mixture, okay, and entering from pump you see lean, this is lean mixture, okay. So rich mixture coming out, it is going to flash chamber or flash tank, extra hydrocarbon if it is there, you are taking out that hydrocarbon. Hydrocarbon is large longer chain hydrocarbons, so you are not selling that one with gas, you may sell separately, okay. So that long chain hydrocarbon you are collecting here, okay. So that is not our purpose at this moment. Our purpose is to remove H2S and CO2 basically. So that flash tank fluid is coming to some filter, then heat exchanger section. The heat exchanger section I told that heat will be exchanged with lean and rich mixture, and this will be producing your lean amine, okay. Lean amine is being produced. Okay, how it is producing? You increase temperature and do the reverse reaction, okay. So you are producing lean amine. So lean amine exiting here, you see from bottom, it is going to heat exchanger and it is going to booster pump. So everywhere pressure drop will be there. So every time you need one pump to increase pressure, so that fluid will be flowing with certain whatever required pressure. Then again you are passing through one filter, then amine cooler is here, okay. You are reducing amine temperature, again you pump, you put into your absorber section, okay. Some other systems I am not showing here because other system supporting system actually. For example, that inlet sour gas is there, so there will be some inlet separator. So I am not showing, I am not discussing now at that point. So my main focus is absorber and steel or that reboiler section where you are separating H2S and amine, okay. And whatever sour gas you are getting, sour gas or acid gas here, okay, it is coming through this reflux condenser and it is going like this, okay. So then you can remember the loop. It is coming from contactor column, flash chamber, then heat exchanger, then reboiler section, then again heat exchanger, because heat exchanger will be one common area. It is going to pump, then again further cooling, again contactor column. So this cycle fluid flow cycle you should remember, okay. So based on that I can give some questions. So how this fluid will be flowing from where to where, and you see this lean rich mixture is coming from bottom, entering from top. So those things also you should remember. So actually you should draw this picture and you should remember how this fluid is flowing from one point to another point, okay. And here one more point is there, sweet gas. So sweet gas is here, sweet gas implies there is no H2S and no carbon dioxide. Now before we go for one calculation, we should go through the formula LMEA, okay. So this formula is taken from your book Arnold and Morris, okay, volume 2, okay. So one chapter is there on gas sweetening process, so you can see this formula. So LMEA equals 112 Qg MF divided by C rho AL. So what are the terms? So LMEA is the MEA circulation rate. Okay. Qg is gas flow rate, and Qg for unit is MMSCF. mmscf. D also will be there per day. MEA circulation rate GPM, okay, and MF is your total acid gas fraction in inlet gas, total acid gas fraction in inlet gas, moles acid, how many moles acid divided by moles inlet gas, okay, and C is amine weight fraction, okay. There is LB, pound amine pound amine divided by pound solution, okay. So weight fraction rho, rho is solution density, this unit is LB pound per gallon at 60° Fahrenheit, and AL is given, AL is acid gas loading, acid gas loading. So there is mole acid gas by mole amine, okay. So this is LDA. LDA formula is like this, only the 192 this term, constant term is changing, okay, other terms are all same. And okay, so ignore these two equation now, later if we use we will explain. And vertical separator gas constant formula, so this formula actually you have seen for your separator design, okay. D mean square 5040 TZ cube G divided by P rho G rho L minus rho G CD dm power half, okay. So this formula is given in volume 1 of the same book, Arnold and Morris volume 1, okay. So this derivation and some problem also I think we have solved in previous lectures, so you can go through this for this formula, okay. So problem for amine treating using for gas sweetening process. You see the problem, a natural gas flowing 100 mmscf at 1000 psig. So psig is given, so psi A if you want to convert, so 1000 divided by 14.7, then it will be psi, okay, absolute. Inlet gas contains carbon dioxide 4.03%, H2S or hydrogen sulfide 19 ppm. You see these two different way I have given, so you have to convert, actually you have to make single type. It is being treated by amine process using DEA, dimethylamine. The outlet gas contains carbon dioxide of 2% and H2S 1/4 grains per MSCF. Okay, so I'll explain that one. What is grain? Grain unit. So grain unit is of mass, like 1 grain. Grain equals 64.8 milligram. So 1 gram equals 15.4 grains. Okay, so many people can use grains also, so that's why I have given grains term, so that you should be familiar with the term. This is unit of mass. Okay, because to solve this problem you have to assume certain value. So I have given that value. Many cases you have to reiterate and you have to calculate. For example, you have to calculate CD, drag force, Reynolds number. So instead of going through that route, I have given just drag coefficient. You can use this one. Okay, fluid droplet size 150 micron, compressivity factor 0.87. Again, you can get from table, chart or table. Okay. Gas viscosity also you can get from chart 0.018, but I have given because to simplify these things. Solution density I have given, number of trays 24. So, normally 20 or 24 trays will be using, people will be using. So, I have given okay use 24 so that I will get unique answer from everyone. Tray spacing 24 inch. So, one tray, two tray, in between space will be 24 inch, so 2 feet. Amine circulation safety margin, say this safety margin is like this. Say if we need 100 liter amine, so it will be 10% safety margin, means 110 liter you have to use. Okay. So, some loss and other thing you are considering. So, from calculation if we get 100, then you have to say you have to buy 110. Okay. Use this equation. So, already I told this equation 192 Qg/mf C rho L. So, you have to calculate the flow rate DEA, the tower diameter, height and reboiler heat duty. Okay. The terms also explained here. I already told you that LDA, DEA circulation rate, QG gas flow rate, MF total acid gas fraction, amine weight fraction, rho solution density, AL acid gas loading. Okay. So, these some values will be given. For example, C value 35% is given here. Okay. If it is not given, actually you have to go through other chart and table from their reference. But for problem purpose, normally I will give. Okay. So that everyone should get unique answer. If I give chart or something, then there will be issue. Then I have to give chart also. Okay. Just I made simplified. And now how to solve it? Yeah. For this problem, total acid gas inlet equals 4.03 carbon dioxide already given, and H2 is given 0.19 ppm. Okay, 19 ppm if you convert into percentage, it will be coming like 0.0019. So, total 4.032%. Okay, total acid gas inlet. So, carbon dioxide and H2S plus CO2. Okay. So, CO2 exit this, then inlet partial pressure for acid gas, it will be like this 1015, because 1000 plus 14.7, or you can write 14.7. Okay, 2 divided by inlet acid partial pressure equals inlet acid partial pressure equals 4.032 divided by 1000. So, it will be giving 40.9 psi. Okay. And outlet partial pressure of acid 1014.7, and exit acid is 2%, 2 divided by 1000, it is coming 20.3 psi. Okay. This partial pressure. DEA calculation. DEA. Okay. Anything wrong? Oh, fine. Just wait. DEA calculation formula given. Okay. So, for DEA calculation, rho given 8.71. Okay. Solution density of DEA, C given 0.35 lb per lb, AL given 0.50 mole per mole. Okay. So, you have to remove the formula. So, formula whatever definition is there, based on the data is given. Direct formula actually. MF equals 4.032%. So, it is coming 0.04032. So, LDEA equals 192 into 100 into 0.04032 divided by 0.35 into 8.71 into 0.5. Okay, so this is giving 508 GPM. Okay. Now, safety margin. safety margin. So safety margin for DA 10% is given. So now LDA equals 508 into 10%, so 1.1 multiplication. So it is coming 559 GPM. Okay. Now tower size. Tower size formula D square equals 5040 formula you have seen already. TZQG divided by P rho G by rho L minus rho G CD by D dm square dm this is not here, this is here, power half. Okay. So CD value given here 0.74, dm value 150 given, T value is given 560, 100 plus 460, Z is 0.85, then Z is 0.87 I think, and P 1000 plus 14.7, and rho L rho G equals 2.7 SG into P by TZ. Okay. From there, if we put data 2.7 into 67 into 1014.7 divided by T 560 into 0.87. So this is giving 3.77. Okay, and rho L is giving 8.71 lb per gallon, or 65.1 lb per cubic feet. Okay. So finally D is coming 79.4 inch. Okay. So you put all this rho L rho G value, then finally D will be calculated as this. Now reboiler duty. Reboiler duty. So using 1000 BTU, British B capital, BTU per gallon lean solution. So Q or heat transfer will be 1000 into 559. We got this that much of amine required, 559, and 60 minutes per hour you have to calculate. So into 60. So it is coming 33.5 MMBTU per hour. Okay. So reboiler heat duty, how much heat will be required for in reboiler. Okay. So some heat you can recover, some heat you can not recover. So if you assume that we are recovering some amount, then again you have to do more calculation. Okay. So for simplification, just you should get idea. Okay, this much of heat will be required, and this amine will be flowing to your absorber. It will come again, reboiler, again it will go to absorber. So the circulation will go on. Okay. Some extra acid, whatever you are producing, so that acid will get separated, and you can reuse or you can dispose. Okay. Okay.